When we first started talking about complex numbers, remember that we began by defining an imaginary unit I, and I was very simply the square root of -1. And it opened up a whole new room of mathematical treasures for us. Well, here we're going to kind of do the same thing, except our dilemma at this point, rather than our dilemma being one of not being able to take the square roots of negative numbers, which led us into the complex world to begin with, our dilemma now is to have some reality for complex numbers. That is, we can't at this point put complex numbers onto a coordinate plane. But if we make a very simple definition, we can do that. Here's what we'll do. We'll take a coordinate plane and we'll define the horizontal axis as the real axis and the vertical axis as the imaginary axis. And that's all we need to do in order to find a point corresponding with a complex number like 5 plus 3i. Now remember that in this complex form we have a real part and an imaginary part. And that corresponds well with our real axis and our imaginary axis. And here's how it works. It's that on the real axis we are going to go a distance of 5, and on the imaginary axis a distance of 3. And it corresponds exactly as it would if we were dealing with real numbers. So it's 1, 2, 3, 4, 5, and then up 1, 2, 3 for this point. Now, this is the point then that is 5 plus 3i, and it is the point in coordinate form 5, 3, like this, as we might expect using real numbers. But now, then think about it in complex form here. It's really 5 plus 3i. Now, here's what we want to talk about as well. We want to think about the notion of distance from the origin. And to think about that notion, we're thinking about this distance 5 and this distance 3. And we know that this distance can be found by just taking the square root of the sum of the squares of those distances. And that's really what we're going to do here. Now, we're defining that distance to be the absolute value of the complex number that we're talking about. So it's the absolute value of z. And that absolute value of z is found by taking the square root of the sum of the squares of the 5 and the 3. So this would be 25 plus 9, 34 under the radical. So this distance then is the square root of 34. Again, as we would expect from our work from the past. Okay, now here's what we're going to do with this. Oh, before I get to something else, let's take another point. What about a point that I might define as z subscript 2 as negative 5i? Now, negative 5i, you know, there's no real part. So for the real part of our coordinates of this point, it would be simply 0. So we go 0 left and right, and minus 5i on the imaginary axis puts us down at 1, 2, 3, 4, 5 in this negative direction. And this distance is calculated the same way. Square root of 0 squared plus negative 5 squared, gee, that's 5 squared, that's 25, this distance is 5. And we would expect that because of the distance that we see here. Okay, now, let's, with this definition, think about another idea. Now, this other idea has to do with a trigonometric form for defining this distance, or excuse me, defining this point. Now, this is the point AB, let's say, and it corresponds with the complex number A plus BI. Now, this distance would be A and that distance B. A would be negative, but that's not terribly important at the moment. Now, to find this distance, we know that we take it's the absolute value of this, which is the square root of A squared plus B squared. All right, that's fine. And we're going to call this distance R. But and we'll calculate it in just a second. But here's what we're going to do. We're going to describe the position of this point that we've plotted in an entirely different way from the notion of horizontal and vertical distance. The trigonometric form is a form where we're going to use an angle and a distance along a ray in order to describe the position of that point. You see, suppose we can describe this angle as an angle theta. And then once we have that angle, we have a ray just going out here infinitely far. And if we can describe a distance along that ray as r, then we can describe that point in terms of an angle and a distance rather than horizontal and vertical distances for the exact same point. This is a pretty big leap mathematically for us. But okay, so that's what we're going to end up doing. Let's calculate r. Now r is calculated as we would expect in terms of a and b. It's the square root of a squared plus b squared. So this then is the square root of a squared plus b squared. All right, now theta, we need some way of describing theta. Well, gee, what about that theta? Well, we know that theta is related to this reference angle within this little right triangle. And using the b and the a idea, we're talking about a tangent notion. So the tangent of theta is b over a. So that's how we arrive at theta. So let's talk about the two ideas. From this a plus bi form, we can identify r and theta using these two, I guess we could say, formulas, these relationships. R is the square root of a squared plus b squared, and the a and the b are from here. And the tangent of theta is simply b over a, and the b over a is found here. And it's important to make that relationship back to the complex form because you're just fitting a pattern here at this point. So the b and the a are found in the complex form, the a and the b here found in that complex form. Okay, so now we have a new way of describing positions on a coordinate plane. And this is called trigonometric form, and it's also called polar form. We may see why that's the case a little bit later. Okay, now that we're able to go from sort of a coordinate form to a which we might call standard form, to a trigonometric form, let's think about going in the other direction. Suppose we know the r and the theta here, and we'd like to make the calculation for a and b. Well, let's see. Now, we can use our trig ratios to help us with that. Come back, let's slide back over here just a little bit. Now, we know that if we know theta and we know r, and we have this little reference angle here in the triangle, that we can be thinking about a b over this, the sine, you see, of this angle in order to get b, and we can talk about the cosine of this angle in order to get a. That is, the cosine of the reference angle for theta. I'm thinking of both of these sort of simultaneously. Maybe I can call one of them theta prime to be absolutely accurate here, but I think there's just a locked relationship between these two. You have the angle here, you automatically have that reference angle in the little right triangle that we use for these calculations. Okay, so we have the cosine of theta then is a over r, and let's see, a that multiplying by r on both sides, we find that a is r cosine theta. And that's a very important relationship here. To find a, we use r and theta. Just like to find r and theta, we used a and b, you see, going in sort of the other direction. Okay, so a is r cosine theta, and in a similar way, b is r sine theta. So a is calculated as r cosine theta, b is calculated as r sine theta, and then we can put our a and b into the complex form. So a plus bi would be a plus b times I. Now normally the I is not written as a coefficient way out here. It's written a little bit differently, and in fact the R is often factored from these two from these two terms as a common factor. So it's a lot of times it's written as R times cosine theta plus I sine theta. Now, by the way, the R is sometimes called the modulus in terms of vocabulary for this kind of form. R is called the modulus, theta is called the argument, modulus and argument. We're not going to use those fancy words very much, but they occasionally come up, maybe in the textbook from time to time. Suppose we want to write this complex number in trigonometric form. Well, the trigonometric form is this form. It's the form r times cosine theta plus I sine theta. And we need a value for r and theta, you see, in order to just plug in here. And we have relationships that allow us to make that calculation. Now notice the a and the b here are the -5 and the 3. So in calculating the r, it's the square root of a squared plus b squared, so it's -5 squared plus 3 squared. Gee, that's the square root of 34. And we use tangent theta as b over a, you see, for the calculation of theta. And we find that, let's see, b over a, we're looking at the b and the a involved in the complex form, so it's 3 over -5. And inverse tangent on -3/5 gives us a theta of approximately -31 degrees. Whoa, -31 degrees? Now wait a second, we're thinking about theta as a positively measured angle somehow. And we have to consider that when we take inverses of trigonometric in the trigonometric form, that we may get angles that appear in quadrants that we're not interested in, and we have to make some kind of adjustment for that. All right, so we need to think about this rather carefully. Let's come over here and think about where this point would lie in our coordinate plane. So in our coordinate plane, we're thinking, let's see, -5, 3. Oh, so this point then is in the second quadrant, and so we're talking about an angle here, and yet we've calculated theta as an angle down here. See, this is the theta that we've just calculated. In order to get us to this position, we need to simply add 180 degrees. So we're saying then that the theta that we're interested in is -31 degrees plus 180 degrees, and that gives us 149 degrees. So now, with the r and the theta, we can come back over here and write our trigonometric form. The r is the square root of 34, and theta is 149 degrees. And this is our trigonometric form. And that really is all there is to it. You just pop this information about A and B into our relationships for the calculation of r and theta, and be sure to consider the position of our point in our coordinate plane, because when we take inverse tangent, sometimes we arrive in a quadrant that we're not interested in. So we just have to take that into consideration. Okay, so here's the trigonometric form. Now it's pretty easy to verify your calculations here using the calculator. If you want to, for example, you can do this. If you take the square root of 34 and multiply times cosine of 149 degrees, you should get this -5. You should get right about -5. And the square root of 34 times sine 149 degrees should give you the 3 for the coefficient of I. You might try that on your own. Let's take a complex number now written in trigonometric form and write it in standard form. We start with our problem written in trigonometric form, and the important thing is to identify the r and the theta. And with r and theta, we can make the calculations for the a and b in the standard form. A is r cosine theta, b is r sine theta, and that's really all there is to it. It's not a really big deal calculation here. R 3 over 2, and the theta is 300. And now cosine of 300 degrees, and we might begin to think, well, gee, a 300-degree angle is in the fourth quadrant. The reference angle is 60 degrees, and in the fourth quadrant, cosine is positive, so cosine of 60 degrees is 1/2, so it's positive 1/2. So it's 3 over 2 times 1/2, or 3/4 for the value of A. And in a similar way, we find B, r sine theta, 3/2 times sine 300 degrees. Sine of 300 degrees, the reference angle is 60 degrees. The sine of 60 degrees is square root of 3 over 2, but in the fourth quadrant, sine is negative, so it's negative square root of 3 over 2. This becomes negative 3 root 3 over 4. Now, with those values for A and B, we just plug them into this standard form. The A was 3/4, and B negative 3 root 3 over 4 as the coefficient of I. There are a couple of calculations or a couple of operations we want to talk about involving complex numbers that are in trigonometric form. It turns out that we have a formula for the multiplication and division of complex numbers in trigonometric form. Now, I'd like for you to look at those in your textbook and refer kind of back and forth from the video to the textbook and so forth. But here's the way it works. We have a couple of numbers in trig form, and it looks pretty complicated, but it's really easy. Here's one number in one complex number in trigonometric form. We're multiplying this number times another complex number in trigonometric form. And we're going to use this formula. And we could actually derive this formula if we wanted to do that. We could go through this multiplication process, and it gets pretty algebraic intensive when you do this, but you'll find that this is what comes out of it. That is, we can use our cosine of the sum of angles and sine of the sum of angles identities in order to make replacements in this multiplication process. But in the day-to-day multiplication of complex numbers in trigonometric form, we'll just use this as a formula. Now, notice the multiplication of the R values. We're multiplying modulus values. We're multiplying moduli. Okay, so it's just identify the modulus for each one, multiply those rascals, and then it's the cosine of the sum of the angles involved. So you just identify the angles involved. We have 140 degrees in this complex number in trig form and 60 degrees over there. So it's 140 plus 60, and over here plus I sine of the sum of the angles, which is also 200 degrees. So then here is our answer. And notice that what we're doing is we're taking a couple of numbers that are in trigonometric form. We're multiplying them, and we get a result which is a value in trigonometric form. All right, now let's talk about division. Now we're going to take this complex number in trig form and divide by this complex number in trig form, and we're using another formula. Now, there's a great similarity between the two formulas. In the previous one, when we were multiplying, we multiply the R values, and here we're dividing them. It kind of makes sense. In the previous one, we had the cosine of the sum of angles. Well, here we have the cosine of the difference of angles, and here the sine of the difference of angles. So there's kind of some symmetry here in the two different ideas. Well, at any rate, we just plug into the formula to get our answer. We're dividing these R values. They come from up here, so it's 12 over 3. Now we have the cosine of the difference of the angles, and the order here is very important. Before, when we were adding, order is not terribly important, but here when we subtract, it's very important. This is the theta, the angle in the numerator, and this theta is the angle in the denominator. So this is 52 degrees minus 110 for our problem in both places here. Let me close this bracket. And 12 over 3 is 4. When we collect here, we get negative 58 degrees, and also in this place. Now, in some settings, I suppose it might be okay to leave this angle as a negative angle, but I think it's probably better to write it as a positive angle, and the angle coterminal with this one would be the angle that we find by just adding 360 degrees. So you take negative 58 degrees, add 360, and we get an angle of 302 degrees. So here's our answer as the quotient of these two complex numbers in trigonometric form. Here's our complete answer. A rather interesting pattern emerges when we take a complex number in trigonometric form and apply an exponent to it. Suppose we start with a z in this standard form, the standard trigonometric form, and we simply square z. It means we have two factors like this, and we can string them out and just think about our multiplication operation. R times R would give R squared, and then multiplying the other parts, we get, let's see, theta plus theta. Well, that's just 2 theta, you see. And for sine, it's 2 theta. And it turns out that the 2 here in the squaring corresponds with the 2 here and the 2 here. And that pattern would continue. If we had 3 factors of z, then this would be r to the 3rd power, and we would have 3 theta here in this the binomial form. And most generally, z to the nth power means take this complex number in trigonometric form and raise to the nth power. Well, it's r to the n times cosine n theta plus I sine n theta. This is called de Moivre's theorem. De Moivre's theorem. De Moivre's theorem is really helpful if we're taking a complex number and raising to some exponent, and that complex number may be in standard form. For example, if we have -1 plus I to the 10th power, you see, if we want to evaluate this, what we would ordinarily have to do is, well, one of two techniques would be appropriate here. We could write the 10 different factors, 10 binomial factors, and string them all out. And we would have a truckload of terms to collect and deal with. And another way would be to apply ideas from the binomial theorem. But what we can do here, the most efficient way, is to identify the r and the theta and go into the trigonometric form of the complex number like this. Let's see the r. That's square root of a squared plus b squared. A is the -1 here, and b is the coefficient of I, understood to be 1. So the square root of 2 then is r. Tangent theta is b over a, and that's 1 over -1, which is -1, and the inverse tangent for -1 is -45 degrees. But we'd like to have an angle that is in the appropriate quadrant for our complex number. If we think about this, let's see, -1, then 1. -1, 1, gee, that's a second quadrant angle. So to put us into that second quadrant, we take the -45, add 180, and we have 135 degrees. So here's our r, and here's our theta, and away we go with our complex number in trigonometric form. So the r becomes the square root of 2, theta 135. Now, if we want to raise this z to the 10th power, we simply take the r and raise it to the 10th power and multiply the angle times 10. You see, it's 10 times theta. So it's 10 times 135, and just evaluate from here. Now, the easy way to deal with the radical is to think of the radical in terms of a fractional exponent. The square root of 2 is 2 to the 1/2 power. And when we raise powers to powers here, 10 times 1/2 is 5, and 2 to the 5th becomes 32. Now, I've kind of stayed with this, the flow of the r value and the expansion of that. Let's turn our attention now to the 10 times 135. Well, that's 1,350 degrees. Now, if we were dealing with this on the calculator, just pop this into the calculator and we get a value right quick. But we can think of this as an angle which has a coterminal counterpart. So we can find coterminal counterparts by subtract 360, subtract 360, subtract 360. You see, and subtracting 360 enough times puts us into the first circuit of our evaluation for theta. It turns out to be 270 degrees. And the cosine of 270, if you think about the evaluation of that, think about the graph maybe, we find it to be 0. And the sine of 270 degrees is -1. So this is simply -I times 32, or -32I. A lot easier than writing 10 factors of that binomial and trying to expand. Here's another one. Now, here we have our complex number is already in trigonometric form. We're raising to the 10th power. We need to understand here that the r is kind of understood to be 1. We could think of this as 1 to the 10th power. And so our z to the 10th, we're thinking of as the r times this. And here's our theta is 5 pi over 4. So generally, z to the 10th power is r to the 10th times cosine 10 pi, cosine 10 theta plus I sine 10 theta, and just plug in the given information. Now r, as I mentioned, was understood to be 1, so this is 1 to the 10th, and here we have 10 times our theta of 5 pi over 4, and again over here. Now the 4 and the 10, we have a nice cancellation, leaving 5 in the numerator. 5 times 5 pi is 25 pi over 2 in both places. And then we think of the coterminal idea here. Well, gee, when we're dealing with pi's and so forth, it's a 2 pi is a complete period. And so we can subtract 2 pi again and again and again. Well, what do we have here in terms of the number of pi's? Well, 25 over 2, that's 12.5 pi. You see, subtract 2 pi, 2 pi, 2 pi, 2 pi, subtract 12 pi, and we're left with 1/2 pi, or pi over 2. So this is cosine pi over 2 plus I sine pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So this is very simply I for our answer. Another situation where the polar form comes in handy is to find the nth roots of a certain expression. Now, the situation might be posed like this. We want to find the sixth roots of 1, and the request could be made as what numbers to the sixth power is equal to 1? Or we want to solve the equation x to the sixth power is equal to 1. Now we're going to show the process of solving this using the techniques we've already learned about, and then we're going to apply a kind of pattern involving polar form. But if we were looking at this just prior to this study of polar form, we would think, well, we have a 6-degree polynomial function. There are exactly 6 zeros in the complex number system, and let's go about finding them. We would try first factoring, and let's see, we have the difference of squares here, so this factors into x cubed plus 1 times x cubed minus 1. But we can factor the sum of cubes and the difference of cubes, so let's go up here and do that. X cubed plus 1 factors into x plus 1 times x squared minus x plus 1, and x cubed minus 1 factors into this linear factor times this quadratic factor. And then each of the quadratic factors we would intend to factor a little further. Well, we can't factor those any further, so we'll have to apply the quadratic formula to find the 2 zeros that appear here and the 2 that are in this factor. So once we've done that and the smoke clears on all of the manipulation, we find our 6 roots to be x is -1 coming from this factor, x is 1 coming from this factor, and then two zeros are involved in this expression and 2 zeros here. Now do notice that our complex zeros occur in conjugate pairs here because we're dealing with a polynomial function. Okay, now is another way to attack the situation, and it involves a rather intriguing use of polar form. It works like this. If we have a number that is in polar form, then we can find the nth root of z, which is the nth root of this expression, by using this pattern. It is the nth root of r times cosine, now notice we have theta up here, but it's the cosine of this fraction, theta plus 2 pi k, I'll tell you about k in a minute, over n. Now the n is the same as this nth root business. You see, if it was the 4th root, that would be a 4, 6th root, that would be a 6, and so on. Okay, and then the same fraction occurs over here with sine, as we might expect. Now k is simply a little counting mechanism, and k takes on various values up to n minus 1. Now k starts at the value 0, and it goes up to n minus 1. And it turns out that all of these roots will occur by letting k take on a separate value each time. Now notice there are n different values that k takes on here, and there will be n values for this nth root notion. All right, let's take a problem. Suppose we're talking about the problem we had before. Now, with this problem we had before, this idea of the 6th roots of 1, well, 1 is not in complex form. Let's write it in complex form. So the z we're talking about is 1 plus 0i. Now, let's put it into polar form. All right, polar form. We need an r and a theta. So r is the square root of 1 squared plus 0 squared. Oh, that's simply 1. Then to find theta, we use tangent theta is b over a. Well, it's b over a. That's 0 over 1, or 0. Let's see, inverse tangent of 0 is 0 degrees. So theta is 0 degrees. So we have an r of 1 and a theta of 0 degrees. Sounds like a really degenerate kind of expression in polar form. So it's 1 times cosine 0 degrees plus I sine 0 degrees. Now, we apply this idea, this pattern, like this. We think, okay, the notion is that we want the 6th root of z. I'm going to go ahead and replace this with a 6. We've already talked about the general case here, but this specific case involving the 6th root of z is the 6th root of the r. The 6th root of 1 is just 1. It'll kind of go out here. Times the cosine of the angle theta plus 2 pi k over 6. Now the 6 is corresponding with this 6th root idea. All right, and then the same fraction appears over here. And then we let k take on values 0 through 5. So away we go. We say, all right, let's let k be 0. If k is 0, then we look at this and we have, all right, if k is 0, then this term goes out. We have 0 over 6. Oh, that's the cosine of 0. And then the same way with the sine. The really nice thing about this is that once you evaluate for one of these fractions, you have automatically evaluated for the other. So you can kind of bring down in a lot of situations. So we have, let's see, the cosine of 0 plus I sine 0, and the cosine of 0, you see, and then the sine of 0 turns out to be 0, and that turns out to be 1. So we have 1 as one of the 6 roots of 1, as we found before. We found 1 to be one of those guys. Now, if k is 1, here's what happens. We have a 2 pi times 1. So we have 2 pi in the numerator, 6 in the denominator, 2 pi over 6, oh, that's pi over 3. So the fraction here becomes pi over 3. And over here also pi over 3, so it's cosine pi over 3 plus I sine pi over 3. Cosine of pi over 3 is 1/2. The sine of pi over 3 is the square root of 3 over 2. And now writing this with the common denominator, it's 1 plus root 3i over 2. And that's one of the items that we had before. And then we come back over here and let k take on the next value, 2. And if k is 2, here's how we evaluate. We come up here to this form, and we let k be 2. 2 times 2 pi, 4 pi. 4 pi over 6 reduces to 2 pi over 3. Both fractions then are 2 pi over 3. Cosine of 2 pi over 3, think about it a little bit, it's negative 1/2. The sine of 2 pi over 3 is root 3 over 2. Using our common denominator here, we have negative 1 plus root 3i all over 2. Again, another one of the zeros that we found earlier. Well, then we let k take on the other values, the values 3, 4, and 5, and that will give us all 6 of the 6th roots of 1 using this notion. Let's go through another problem. Now this one seems a little more complicated, but we want the 4th roots of the z equals this. Now, you know that if we face problems that are in the typical complex form, then we change them into the polar form. If we already have a problem in polar form, we don't have to make that transition. So here we just go right into the idea of the 4th roots for this. So it's the 4th root of z, and following the pattern that we established before, it's the 4th root of 16 times, let's see, and now we go through this idea of the theta plus 2 pi k over n. You see, so it's this theta plus 2 pi k over the n, and the n is 4, and the same fraction over here with sine. And now we let k take on values. Well, if k is 0, then we look up here and we evaluate that situation. We have 2 pi times 0. That goes out. So we have 4 pi over 3 divided by divided by 4. But dividing by 4 is the same as multiplying by 1/4, and this fraction times 1/4, the 4's would go out and we would have pi over 3. So we have 2 times, you see the 4th root of the 16, it gives the 2 times cosine pi over 3 plus I sine pi over 3. Cosine pi over 3 is 1/2. Sine pi over 3 is the square root of 3 over 2. And now we multiply through by the 2, and these denominators go out, so we have 1 plus the square root of 3 times I. Okay, that's one of the 4th roots of this complex number. Now, in some situations, it might be okay, since we started with a number that is in polar form, to give the solutions, the nth roots, you see, in polar form. So this might be an appropriate answer to this problem. I'm going ahead with another step or so to evaluate a little bit farther and take it into a different kind of simplification, if you will. All right, then if k is 1, you see k is going to take on values 0, 1, 2, and 3 in this evaluation process. If k is 1, we look up here and we let k be 1. So we have, let's see, 4 pi over 3 plus 2 pi times 1. That's 2 pi. Now for our common denominator here, it's 3. So we think, let's see, multiply by 3 over 3, and we have 6 pi over 3. 6 pi over 3. plus 4 pi over 3, that's 10 pi over 3. 10 pi over 3, oh gee, I need to think about this a little bit more. You see, you're not gonna be able to think through all of these. I know that I can't. I have to go out to the side and kind of evaluate a little bit, kind of like this. I have, let's see, I'm just using the fraction part now. It's 4 pi over 3 plus 2 pi all over 4. And really there are a couple of ways of dealing with this complex fraction. One technique, by the way, that might work pretty well is to multiply here by 3 over 3. You see, if I just multiply this by 3 over 3, then in this big numerator I'll have a cancellation with that 3, so I'll have 4 pi plus 6 pi over 12. Let's use that technique. 4 and 6, that's 10 pi over 12, which reduces to 5 pi over 6. Another technique would be to just collect these, find a common denominator, collect these, and do this 1/4 idea. But let's see, 5 pi over 6 then, so we slide back over here, and this becomes cosine 5 pi over 6 plus I sine 5 pi over 6. The 2, notice, remains the same for all of these because it's the 4th root of 16. All right, then we go through a little evaluation process. The cosine of 5 pi over 6 is negative square root of 3 over 2, and then the sine of 5 pi over 6 is 1/2. So then multiplying through by 2, these denominators go out, and I have negative root 3 plus I as another of the 4th roots for that expression. And once again, this is a valid way to write our this 4th root, and this is another valid way to write that 4th root. And we would continue the process letting k take on values 2 and 3 for the other 2 of those 4th roots of that expression.